things moving forward here. Newton's third law, action and reaction. In the pictures below, a student pulls on a rope that's attached to a wall or held by a strongman. In both cases, the scale reads 500 newtons. In which case is the student pulling harder? Brad.
The one with the caveman guy.
Why?
Because the wall is just holding it there, while the caveman guy is like pulling it back. He's like wanting it to go like further, while the wall's just keeping it in place.
Okay.
Because like the guy's pulling against him, the wall isn't like pulling against him, it's just keeping it in place.
Okay. Interesting thought. Okay, so if we look at the forces, yes, there's tension on both sides. If we look at the action-reaction force pairs, when the kid is pulling, kid pulls this way, at that intersection between his hands and the rope, there's a force pulling back on the kid. And then here, where the rope hits the scale, there's going to be a force that way on the scale, but there's going to be a force this way on the rope. Same thing here. There's a force this way and a force this way. And then here, there's going to be a force this way and a force this way. It doesn't ask you to draw all the pairs, but if it did, these would be all of the pairs. Now, in this scenario, you've got the same set. Should it matter what this object here is? Whether it's the wall or the dude or an elephant or a Jeep, if this reading is the same, 500 newtons, 500 newtons, if that's the same in both cases, should this student have to pull differently? I mean, your gut says yeah, because, well, this guy doesn't have to pull as hard because this guy's pulling the other way, is what, I understand why you said that. I've been teaching this for 12 years. I graduated high school in 2005, so I've been a student. I took physics. Yeah, I've been doing this a long time, and my gut still says I want this to be the case. But if we stop and think about it, does it actually matter what's underneath my hand? No, the experience of this guy is the same. So I totally understand, Brad, why you said what you said. But does it make sense to you why that's not true? Because it doesn't matter. Every one of these exists in action-reaction pairs. And if these two numbers are the same, the experience of all of these forces needs to be the same. It doesn't matter what that object is. So in neither case is the student pulling harder. It's the same amount of hardness in each case. Okay, pictured below. Two students kick the same ball at the same time with the same force. If you've ever been in this position, it's uncomfortable. The force pairs, you've got at every intersection, you're going to have a pair of forces acting. Here you're going to have a force this way, the force of A on B, and you're going to have the force of B on A. And here you're going to have the force this way of force of C on B, and then backwards you're going to have the force of B on C. And if the two students kick the same ball at the same time with the same force, that means the force of A on B and the force of C on B, those two are the same. So if these two are the same, what can you tell me about these two? They have to be the same, because if these two are the same and they're action and reaction, so these two are equal and opposite and these two are equal and opposite, it means that all four of these are the same sets of forces, so the net force is 0. And those are all the pairs that you should draw. Every place where there's an interface between different objects is where there's another action-reaction pair. So that's what this is asking you to do too. Given the action force in each picture, so you've got person lifting up on the bar, what is the reaction force if they're just holding it there? This one's an easy one, because you've likely experienced this. Why does the bar want to come back down on that person? Gravity. And if the person's holding it there, these two applied forces, FA1 and FA2, the sum of those is going to equal FG. Which is why it's easier to lift things with two hands, not one hand. In this one, you've got a bowling pin hitting a pin to the right. What's the reaction force? This one's counterintuitive. Sorry? Yeah, you're going to have the force of the pin on the ball. And again, we don't notice. This one you don't notice. The ball is generally speaking a lot heavier. The pin's really light. The pin goes flying and the ball doesn't really seem to stop at all. But there is a force on the ball. If we jacked up the mass of the pin, it would be noticeable. Instead of thinking about this scenario at the bowling alley, think about this scenario at a carnival where they're trying to rip you off. If you've ever done this at the P&E, for example, and maybe you're not bowling but you're throwing, it's pretty easy to see if you just increase the mass of these pins a little bit, the ball stops dead and the pins don't move. But the scenario is the same. You're just playing with some of the variables. There's a force backwards on the ball. And this one's an interesting one. The compressed air pushes outward on the balloon. What's the reaction force to that? Air pushes out on the balloon, so the balloon does what? So there's an elastic force which way? Well, that's this one. The outward force from the air inside pushes out, so the elastic force pushes which way? In. Every single one of these has an equal and opposite force in. The balloon pushing on the air. Because as soon as you untie it right here, you're going to allow it to collapse in. And then the last one, it's ridiculous, but it's trivial. At every interface, there needs to be another action-reaction pair. So if we call these objects A, B, C, D, E, F, and G, I don't know how you labeled it, but a way to do this is there's a force of A on B, but then there's the force of object B on object A. This guy pulls back, but the rope pulls him in too. And every single one of these will have a corresponding pair. It ends up looking like this. The force of object A on B, and then the force of object B on A, B on C, and then C on B, C on D, and D on C, D on E, and E on D, E on F, and F on E, F on G, and G on F. There are 7 objects and 6 pairs of forces acting on all those objects. Comments, questions, concerns? Okay, that is, there's no math. This is the sum total of Newton's third law. For every action, there is an equal and opposite reaction, and it's just counterintuitive is all. Okay. So I told you we're going to alternate back and forth. There's a page in there. I want you to skip it. I want you to jump to here. We've talked about the acceleration due to gravity a few times now. In kinematics, you guys dropped objects. In this chapter, we talked about how the acceleration due to gravity is actually You can think of it as the strength of the gravitational field on or near an object. We talked about how objects that have a mass or create around them this gravitational field. And then we use the example of the moon, the sun, and the earth. For you to figure out your verticals given different gravitational field strengths. So what we're going to do today is we're going to say, okay, we're going to extend that. We're going to say not just really big objects creating gravity and really small objects interacting. We're going to take Newton's universal law of gravitation. This word universal literally means everything. And gravity exists for every object that has mass. Gravity acts between any two objects that have mass. Which you guys have experienced, but perhaps haven't taken to its full extent. The Earth has mass, you have mass. The Earth exerts a gravitational field. Your mass interacting with that field produces a measurable gravitational effect. When you trip, you fall down. If you jump up, you're coming back down. And it doesn't matter where you are on this sphere, you're always going to move towards the center, which is why up and down doesn't make sense. If you go to the other side of the planet, the southern hemisphere, you might think you're down from where you started, but when you jump, you slam back in toward the center. Up and downness doesn't make a lot of sense in space. I will leave you to YouTube that. The same YouTube videos that will tell you it is flat can also tell you why it's round. It's round. I taught a flat earther once. That was a good time. There was no convincing him otherwise. If that was for any one of you who might have a semi-serious question regarding the flatness of the Earth, there is a YouTube video I can direct you to of a die-hard flat earther filming the proof that it is round. Not round even, but spherical. And watching him wrestle with the scenario that he creates that proves exactly the opposite of what he's trying to prove is a good time. And then the video he posts after that is him denying everything he had done previous. It's great. If you seriously want proof of the spherical nature of the Earth, I can provide it for you. I've saved it. I'd have to go look. I don't remember. So, the Earth is a sphere, and gravity acts between any two objects that have mass. Gravity depends on two things. And we can deduce these things relatively easily. Earth has mass, you have mass. If the Earth's mass just went away, there would be no gravity to speak of. If your mass went away, there'd be nothing for you to interact with. So the fact that gravity is a thing depends on masses, or the masses, I'll just forget the word the, masses of the objects, and it depends on one other piece. Does Earth's gravity always have an effect on you? Well, you here on this planet, sure, but what if I grabbed you and I started taking you other places, like the moon? If we ended up on the surface of the moon somehow, would Earth's gravity have the same effect on you? No, it would decrease, but it would still have an effect on you. But being closer to the moon is the thing that would have the dominant effect on you. How do we know that the Earth would still have a gravitational effect on you on the surface of the moon? Well, is the opposite true? Does the moon have a gravitational effect on you here on Earth? How do you know that, Emma? You're right. Would it help me to say you're right? It does. How do you know that? If the moon has a gravitational effect on anything on our planet, that means it has a gravitational effect on everything on our planet. You just don't feel it affect you. But you said, you gave an example of an object that it does affect. What does it affect? The tides. The fact that we have tides is not the water just sloshing around as our planet shakes. It's the moon out there. The gravitational effect on the moon and its mass has a measurable effect on the mass of the water that sloshes around the surface of our planet. The water has mass, the moon has mass. The moon doesn't have enough mass to rip our water away, thankfully, because we'd be dead. But it pulls on it as it moves its way around our planet. The effect of that is a tide. So it doesn't have as great of an effect on you because your mass relative to the mass of all that water is very small. But the effect is still there. It's just not as great. So it depends, gravity depends on the mass of the objects and what other piece? Based on the conversation, this information I've just tried to talk about here. Yeah, so how far you are from the source of the gravity, you bet. So gravity depends on two things, the masses of the objects and the distance between the objects. Mars, for example, as a planet, is roughly the same size as our moon. It's a little bit bigger, but not much. The moon has a measurable gravitational effect. Mars does not. Mars does not create tides. Mars is so far away that as far as our existence here on Earth, if you didn't see that little red dot in the sky, it may as well not be there. So the distance between these objects matters. Well, that was fast. So, based on that information, here's what Newton's law of universal gravitation states. That the force of gravity, we had one expression for it before. We said that Fg was equal to the mass times little g, where little g is the gravitational field strength. But his universal law, we're going to change that a little bit. What he said is that, and I want to give it to you the same way your formula sheet gives it to you. Newton's universal law of gravitation states that between any two masses, I'll say big M and little m, sometimes instead of big M and little m, it's M1 and M2, but it means the same thing. For the two different objects with whatever their masses are, the force of gravity is dependent on those two masses multiplied together, divided by the distance between those objects squared, out to some multiplier that we're going to call big G, which sounds like a rapper, but it's not. So, this was deduced experimentally. He didn't just sit down and be like, I think this to be true. I mean, some of it you can. We said it already. We deduced a little bit of this already. We said that the gravity has to depend on the masses of the two separate objects and the distance between them. Did we know that the distance had to be squared? No. Did we know that there was some multiplier out there? No. So Newton deduced at least part of this equation and then went out and experimentally verified. For our experience with gravity to be true, this is the way they have to relate. These two multiply, and then you divide by the distance between them squared, and then there's this multiplier that has to exist outside called big G. And for any two objects that you pick anywhere in the universe, this relationship holds, which is weird, but it works. So let's label what these things are. Big G, we call the universal, that's an S there, gravitational constant. That value is true anywhere in the universe, and it is one of the most precisely measured constants in physics ever. It's pretty wild. You do not need to memorize the value. The value is on the front of your formula sheet. It's right here. The gravitational constant is this number, 6.67 times 10 to the negative 11. It's very small. You don't need to memorize it. It's on the front of your sheet. But we'll put it right here. 6.67 times 10 to the negative 11. And the units on that thing are Newton meters squared per second squared. They're weird units. Those have to be the units for it to make sense. And this is experimentally verified. Big M is the mass of object 1, whatever object 1 is. And little m is the mass of object 2. And again, sometimes it's not big M and little m, sometimes it's M1 and M2. Doesn't matter what you call these things. And R is the distance between. And we're going to add a word there in a second. The distance between what? Sire. Yeah, we have that concept for a reason. The reason why we conceptually talk about your center of gravity is not for all of the other wonderful applications that it has. I mean, it does have a lot. For those of you who are athletes, you probably have an understanding of your center of gravity. Because you need it for so many different things you do, especially for those of you who are in physical sports, boxing, martial arts, wrestling. To have an understanding of your own personal center of gravity is important. Gymnastics, oh my gosh, gymnastics is another one. But we call it the center of gravity because if we were to reduce your existence to a single point in space, that center of gravity would be it. It does all of the rest of you outside that point, as far as physics is concerned, doesn't matter. That point in space that is your middle, wherever it is, as far as the calculations go that apply to you, is the only thing that we care about. So this R, this distance here, is the distance between the centers of gravity. And I know I did not leave an abundance of space for you to write that, and I apologize. Your existence can be reduced to a singular point in space. And as far as the math goes, because the math doesn't care about your feelings, unfortunately, as far as the math goes, that's what matters. This just gets really complicated because everyone has a slightly different center of mass. It depends on if you're more muscular or if you are less muscular, where those muscles are and where they're not. How your skeleton is built, where you are more dense, your gender, your biological, not your gender identity, but your biological gender will have different centers of gravity. For those of you who are biological women, your center of gravity is lower, like towards the center of our planet, than any of the biological males here, especially if you've already gone through puberty. Not this guy. Puberty's holding on for Kale. Okay. So let's look at a couple examples of this, and I'll leave you to play with it. Okay, example 1. What is the force of gravity exerted on a 70-kilogram astronaut that is standing on Earth's surface? Well, I'm going to draw a horizontal line here across the middle of this. And below this line, let's look at how we did it before. If I asked you to find the force of gravity of a 70 kilogram person standing on the Earth's surface before today's lesson, what would you do? You would say that the force of gravity is equal to what? What has it been equal to this whole time? Not ma, but mg. Force of gravity is equal to mg, where m is the mass and g is the gravitational field strength. At or near the Earth's surface, what's the value of little g? 9.8. That's a rounded value, but that is approximately what it is for Earth. So we're going to take this mass of the 70 kilogram astronaut, we're going to multiply that by 9.8, and we're going to get the force of gravity to equal what? What is 70 times 9.8? I see calculators, use them. Phones work too. I mean, not on tests or quizzes, but for now they do. Well, 70 times 9.8. Sorry? 686 newtons. Mr. Keeley, what's up? Yes, please. Thank you. Okay. This is what we would have done before 45 minutes ago. Within the last 45 minutes, what I'm trying to convince you of is that not just Fg, but now we've got a universal law of gravitation. So let's use it. Force of gravity now is also going to be equal to this other new expression. Big G times big M over little m divided by r squared. And so we're going to just shove in values for all of these things. If universal gravitation holds, we should get a number that's very close to this one. So let's plug everything in. Big G is going to be 6.67 times 10 to the negative 11. Big M, we're going to call the mass of the Earth, because that's one of the two objects interacting here. The mass of the Earth you do not need to memorize. On your front of your formula sheet, I've got a bunch of constants. It says Earth mass, there it is, and Earth radius, there it is. Now the radius of a sphere is the distance from the center to its surface. And so here it is, 6.38 times 10 to the 6, which is 6,380,000 meters. The fact that your center of mass might be 1 more meter above that, does that matter? Does your height matter, given the fact that the radius of the Earth is 6,380,000 meters? No. Your height is insignificant to the solution of this problem, so let's go ahead and ignore it. The mass of the Earth is up here, 5.98 times 10 to the 24. The radius of the Earth we're going to put down here. 6.38 times 10 to the 6. Now the formula calls for us to square this value. So let's square it. This squared is what students forget all the time. And I don't have enough space, so I apologize. Well, actually, we're almost going to do it. What's the mass of the second object? 70. So now I want all of you to practice punching this thing into a calculator. I don't want the first time you punch this thing into a calculator to be when you're working on this stuff. We've got the time, punch it in now. Because these are gross values to punch in. I want to make sure all of you are comfortable doing it. 6.67 times 10 to the negative 11. And all of your calculators are going to do this differently, so punch this in. Get comfortable with the brackets. 5.98 times 10 to the 24. Close the bracket. Nope. Yeah, no, that should be fine. Bracket 70, close the bracket, divided by, open the bracket, 6.38 times 10 to the 6, close the bracket, squared. Now, if you punch this thing in properly, bed mass should do its thing. I want all of you to get comfortable punching that into your calculators. Don't use your phones because I'm not going to give you your phones on a test or a quiz. What's the value? Well, it's not exactly 686. 685.9. May that as well be 686? Yeah. This may as well be 686 newtons. Being out by 0.1 of a newton is effectively meaningless. Sorry, Emma? Okay, any of you who are getting errors, call me over. Let's see what happens. You need to be comfortable with your calculators. Give me a see what you done. Come on.
I just use that. But no. Yo, what? Yes. Just go this, and then put the put 11.
Show me what you punched in. Yeah.
So I don't like this game. Why is it one? I don't know. Can we figure it out? No. Okay. Keep going. You did X10 twice. Oh shoot.
Right. See who you punched in before?
I see. Okay, now we'll do 70. Bracket, and then we have to only bracket the whole top.
I'm willing to bet. Instead of doing a minus sign, you just do this minus sign. No? Because that'll give you a syntax error every time. Well, this instead of this. I don't know, but you punched in a little bit of it. Okay, anyone struggling with their calculators? All of you should got 686.
I don't even know that.
I will answer that question. That is exactly where we're going. Okay, show me what you did.
Bracket the whole top and then bracket again.
Okay.
So you got 6 point,
6, 7,
7, 5, 10.
Hold on. How do you do that?
For the second half.
Okay, yeah, you're good.
We put negative.
Yeah.
That's good. I think it's just for negative.
Okay, keep going.
The bracket, you, what is it,
5.98.
What else do you have? Do you have that?
bracket, another bracket.
Mr. Joe, how are we doing?
X.
Times 10 to the 6.
So, put that, and then you get
Oh, and then squared. The denominator is squared.
all the denominators squared, Caleb.
Yeah, and that's the most common mistake students make is the one you just made. Done. There it is. Love it.
Oh my god. Oh my god.
Yeah.
You got a square too. Oh my
Why?
god.
That's a lot, right? I'd love to know. Why?
Well, because it's not the first day.
Oh my god.
Well, you want to just people something to look at? No, I'm not wasting that much writing. Sorry.
No. You what?
Okay. You didn't swear that. The
Yeah.
denominator
Oh
needs to be squared.
my god. Hey, you know what? Arm wrestling together. Weird angle, Yeah. I don't want to put this.
That denominator has to be squared, guys. Otherwise, it's not going to line up. So, Emma, you asked the question of where we're going next. Why one when the other? Every time we've used this value 9.8, the qualification that I gave was that we were at or near the surface of Earth. Now, that qualification near has everything to do with the fact that this number is massive. 6.38 times 10 to the 6 is the distance from the center. Did you figure it out? It didn't work? Yeah, start it. Yeah, do the whole thing. This number is the distance from the center of the Earth to the surface of the Earth, and it's huge. 6,380,000 meters. So near the Earth's surface, even if you're a kilometer above the Earth's surface, 1,000 meters. 1,000 meters in the grand scheme of 6,380,000 is nothing. But we can get further and further away from our planet. Now we're going to start talking about space. The Earth, in the grand scheme of space, the Earth is insignificantly small. I showed you this last week. I had Brad hold up a little popsicle stick of, what planet did you have? You had one, Ray Reed had another one, and I held up the sun. Oh, Jupiter, I think I gave to one of you. I don't. Okay. So the Earth is insignificantly small on a solar scale, but for our human scale, the Earth is pretty massive. So let's do another example of where this thing falls apart. What is the force of gravity? Here's the second question. What's the force of gravity acting on a 70-kilogram astronaut who is at an altitude of this? Now, all the words we use have meaning. What does the word altitude mean? Height above. Height above what? The surface of the Earth. So, here's what's happening. We have the Earth. The distance from the center to the surface, that distance right there, is 6.38 times 10 to the 6. And now we've got an astronaut that's this far away. The same distance, that is the Earth to the surface, we're putting an astronaut. This distance is another 6,380,000 meters. What's the force of gravity there? Well, I think I can successfully state, and that you would be convinced without a lot of argument, that if we took the radius of the Earth and then added it to the surface of the Earth, we are no longer near the Earth's surface. Is that a pretty reasonable assumption? I don't know how far that word near no longer applies, but I think if we took the radius of the Earth and added it to the surface of the Earth, we are no longer near. So this no longer works at this stage. Let's figure out what the force of gravity is on that astronaut. So because we are no longer near, we have to use universal gravitation. So GMM over R squared. So the force of gravity is going to be 6.67 times 10 to the negative 11. The mass of the Earth, 5.98 times 10 to the 24. The mass of our astronaut, 70, divided by, now what is R going to be? Whatever it is, we're going to square it. What is that value for R going to be in this case? That value in the equation when I first gave it to you, I said R is the distance between the centers of gravity of the two objects. So what is the distance between the centers of gravity of these two objects?
What's the 6.38 times 10 to the 6 plus the radius?
So 6.38 times 10 to the 6 plus 6.38 times 10 to the 6.
Yeah.
The question, Emma, was what value are we going to use for this distance now? Because R is the distance between their centers. Center to surface is 6.38 times 10 to the 6. And then surface to our astronaut is another 6.38 times 10 to the 6. So the value that we're going to shove into here is 2 times 6.38 times 10 to the 6. I mean, if you want to do it with addition, we could too. 6.38 times 10 to the 6 plus 3.68 times 6.38 times 10 to the 6. Or because they're the same, you just double it. So because our astronaut is no longer near the surface of Earth, that value should be reduced. So what is the force of gravity on our astronaut now? This is where all of you who have the sharp calculators are going to be at a disadvantage because you have to punch it in fresh every time. If you have a Casio or a TI, it's not going to be quite as miserable for you. Well, let's punch it in again. 6.67 times 10 to the negative 11, 5.98 times 10 to the 24, 70, close the bracket. We're going to divide that by 2 times 6.38. Oh, nope, don't want that. Times 10 to the 6, and you can't forget to square it. What's the value you get? What is the force of gravity on that person? Ezra, you got a number? 171.4 what? So let's call that 171.5. That's the value you're looking for. There is not no gravity, but it is severely reduced, which makes sense. The further you get away from a massive object, the less its gravity has an impact on you. And this, yes, sir, do what you got to do. And this is true for any objects that have mass. So the natural logical step here is example 3. 2 physics lab partners sit side by side. So let's use you and the person sitting next to you. One of you has a mass of 55 kilograms and the other one has a mass of 65 kilograms. If you guys sit 50 centimeters apart, this number we're going to use as the center to center distance is 50 centimeters. So just to put that into perspective, let's make this awkward for Kale and Kai. Why not? These are close. And Marcus just left, otherwise it would have been Lachlan and Marcus. Here's the question that we're doing. You guys need to get closer together. Keep going, keep going. Oh! Kale, can you move a little bit to you? There you go, right there. Okay, so this is the question. They are now, their centers of mass, centers of gravity, are 50 centimeters apart. What is the force of gravity between Kale and Kai? Do you feel a force of gravitational attraction between the two of you? No, if you wanted to lean out, you could do so with little, like no effort, right? Right? Okay, but let's figure out what that value is. Okay, you can slide back apart. Here it is. The force of gravity between Kale and Kai, 6.67 times 10 to the negative 11. That universal gravitational constant is still there. And really, I should have written down the formula already, and I didn't. My bad. Let's just cram it up here. Fg equals gmm over r squared. Big G is 6.67 times 10 to the negative 11. The mass of Kale, let's make Kale a bigger one, 65 kilograms. The mass of Kai is 55 kilograms. Remember, M and M are just whatever the two masses of the two different objects are. And we're going to divide that by the distance between their centers. Now it's 50 centimeters. Nothing, we don't use centimeters. We're going to take that 50 centimeters, we're going to convert it into meters. 50 centimeters is what? Is 0.5 meters. So this is the value that we're going to use. And we can't forget to square that distance. If you punch this into your calculator, What is the value that you get? What is the force of gravity between Kale and Kai? Number, you got a number? You guys have a value? Sorry, Manette. That's okay. I call her, if it makes you feel any better, I call your sister you all the time in science class. I just did now, yeah. I know, I do it to her in science class as well. I call her your name. Okay, what's your value? So 0 point, and then how many zeros? 1, 2, 3, 4, 5, 6, and then 953? That is correct. That is correct. So some of your calculators may have given it to you in scientific notation. If it gave it to you in scientific notation, it would be 9.53 times 10 to the negative 7. These are the same value. So for all intents and purposes, the force of gravity between Kale and Kai may as well be 0. But is it? It's not. It's there. It's meaninglessly small, but it's there. Cool. Okay. Questions, comments, concerns? Okay. I'm going to leave these for now. We'll come back to them. I want to give you some time to play with the stuff that we've just done. So flip the page. Here's what I'm going to give you for homework. I want you to do the following questions. I want you to do questions 1 to 6. And 11. Now, before you launch into these things, I want to make clear what's going on here. What we've done, all we've done is given you guys an expression for universal gravitational force. The way forces behave still applies. So if you look at question number 11, what question 11 says is this: we have 3 objects. Now instead of 2, we've got 3 objects. Objects A, B, and C. They're each placed 50 centimeters apart in a straight line. A and B have a mass of 10 kilograms. So the mass is equal to 10. This mass is equal to 10, and object C has a mass that's equal to 15. What this question is asking is, what is the net force on B due to objects A and C? So if we draw a free body diagram of object B, what are the forces that are acting on B? Now I want you to answer this. What forces are acting on B in this situation? What? Be specific, Kai. There's a force from A and a force from C. What force of A is acting on B? And which way is it? What are the forces acting on object B? Someone say something. I know some of you have ideas. Okay, I will tell you for the sake of time. You've worn me down. The forces that are acting on B, what you're asked to find is What does the net force on B do to A and C? Well, B is experiencing an attractive force to C. There's a gravitational force on B from C. So what you've got here is you've got a force of gravity from object C. But you've also got a force of gravity on B from A. And these two are acting in opposite directions. Based on the numbers that you see here, which one would you expect to be bigger? You expect C's to be bigger. Object C has larger mass than object A, so you expect the gravity from C to be bigger. Everything we've done up to this point still applies. You need to draw a free body diagram. You're going to calculate what these values are. One of them acts to the right, the other one acts to the left. So which direction do we want to call positive here, left or right? It would make sense to call to the right positive. So then you're going to go ahead and you're going to figure out what the net force is on object B due to object A. I've done the free body diagram for you. For the sake of making things interesting, though, I'm going to add one thing to this question. What I would like you to do, in addition to finding the net force, I want you to tell me what is the acceleration of object B. Find the net force on B and then tell me how it's accelerating, given that setup. Okay, you got 15 minutes, use this time. You can get off Instagram and Snapchat and all the other distractions that we're stuck with and give this stuff a shot. On your market to go.